Hello everybody, welcome. Thanks for the introduction. As I said, I've been working at IBM starting this year in a project that is, the idea is to deploy a solution in top of Kubernetes and using Apache Flink as core of the processing of streaming events. And I will share with you today our experience when deploying this secure Flink cluster on top of Kubernetes. I want to start describing a little bit our use case. So we have multiple sources of data. The data is coming from multiple services, and all this data is being pushed into a Kafka bus. So we perform the processing thanks to Flink, and after that, depending on the kind of events and the kind of processing, we are storing the data in different storage targets, so other services are able to use it. For example, to real-time dashboard and other services. Also, the solution, the idea is that it has to be generic enough to be able to run in different environments. It has to be also highly available, fault tolerant. And one thing that we have to take always in mind, we have to have in mind, is that we work with sensitive customer data. So all the communication that is done between all the cluster components has to be secure. So here we have the Flink architecture for our use case. So we are using Flink 1.5, and the source of data is Kafka, as I mentioned before, and we are saving the data in Hadoop HDFS, Elasticsearch, Kafka again. So I'm sure you are all familiarized with this architecture. It's the general architecture of Flink. But the only thing that I want to highlight here is that we have several points of communication between the different cluster components. So the job manager, task manager, and also the storage of the checkpoints and save points, as well as the submission of the job. So for our use case, we have to make sure that all these communications are secure. So how do we translate this in Kubernetes? So we took as a starting point the templates that are available in Flink documentation. So if you have tried to deploy Flink in Kubernetes before, you may be familiarized with this as well. So I'll be very quick in this explanation. We have here one job manager deployment that will be in charge to maintain always one single replica of the job manager running. So with this, if ever there is a failure on the job manager, Kubernetes will be in charge of deploying a new instance of the job manager. With this, we can ensure the high availability of the cluster. We have as well a job manager service. With this, what we have is that we are able to communicate with the job manager by using a fixed host name. So once we have a service, we can, from the task manager, we can communicate with the job manager using, for example, Flink as job manager as a host name. As well as for the job submission. So when we want to submit the job, we can address this job manager by using this host name. Then we have a task manager deployment. With this, we can deploy as many as task managers as we need. And the other thing that we have, the solution what we use was for the job submission, we are creating a container for each Flink job. So each container will have the jar of the Flink job and will be in charge of submit the job to the Flink cluster. So we have a fixed amount of jobs, and these jobs are endless and stable. So once we deploy the container of the Flink job, we will submit to the cluster, and eventually, if we have a new version of the job, this container will be in charge as well to do the update. So when we deploy the new version, it will take a save point of the job, cancel, and then restart the new version from this save point that we just created. And finally, we have a config map that we use to expose several Flink configurations. As we are running in different environments, we have to be able to specify, for example, the task manager heap memory, job manager heap memory, the amount of task slots, configuration of the checkpoint, etc. So the first thing that we have to do for the security is to guarantee that all this communication between the cluster components is secure. And we do this by configuring SSL for the cluster. So for this, we have to generate certificates for the cluster components. But here we have the first challenge when we deploy this in Kubernetes. And it's that by the nature of Kubernetes, all the pods will have dynamic IPs. And some of the pods, for example, the task manager, we have a dynamic hostname as well. So how do we address that? We see before that for the job manager, we can create a service, and then from that we can address the job manager using a fixed hostname. So we think that we could do a similar thing for the task manager. By default in Flink, all the communication between the job manager and task manager, between one task manager and another task manager, is performing hostname validation. So now we don't have the problem of the dynamic IPs. We can use the hostname validation. We will be OK. So how do we achieve something similar for the task manager as with what we have for the job manager? We will use a stateful set, a Kubernetes stateful set, instead of using a Kubernetes deployment. What are the advantages of this? With the stateful set, we will have predictable host names. So the host name will be in this form. We have the task manager name, followed by a number that is starting always in 0, then 1, 2, and etc. So we have predictable host names. Then, the host name is after we have the service name, then the namespace where we deploy the system, and then the rest of the DNS that Kubernetes uses for all the services. So from that, if we want to issue certificates for the cluster components, for the job manager, we can use the host name that we create for with the service. And for the task managers, we can create a wildcard certificate because we know how the host name are created, and we always have the name of the task manager, and the only thing that changes is the number at the end. So we can add a wildcard here. We need, from this, we have a certificate that is valid for all the task managers. The other part is the pods that are performing the job submission. They also have to use SSL, but the CLI operations they does not perform a hostname validation. So the only thing that we have to make sure is that the certificate that are used by these pods are trusted by the job manager. So we can have certificate authority that is included in the Truststore of all these components, and then from that issue certificate for the job manager, wildcard certificate for all the task managers, and certificates as well for the pods performing the submission of the jobs. But here we have a limitation. The limitation is that these certificates, these wildcard certificates, for the task managers are linked to a specific namespace. So this use case, if you deploy this system in a single namespace, So you can use this solution, or if you want to, each time you deploy in a different namespace, generate again the certificate, so you can continue using the solution. But for our use case, we wanted to be the more generic possible. So the solution that we ended up using was this one. We generate one single purpose certificate, and this certificate we added to a Truststore and a Keystore with this only single certificate, and we distribute this Truststore and Keystore all over the cluster components. So as we have only one certificate that in our Truststore, there is no additional value that the hostname validation would add to this. So we can deactivate the hostname validation here. And from with that, we can deploy our system without any problem. Additional to this, in Flink 1.6, there is additional validation with the SSL certificates. We are performing now mutual authentication. So this is the recommended way to do this setup in Kubernetes. Well, now that we have the certificates, how do we expose that to all the cluster components? So we use Kubernetes secrets. So we create a secret that is including the Keystore and the Truststore that have inside the trusted certificate, as well as the passwords that we use to be able to use this Keystore and Truststore. So when we create secrets in Kubernetes, the values have to be base64 encoded, and then to serve these files on the different pods, we mount it with this syntax. We just have to declare the volume. We say from what secret we want to mount the files, specify the list of files, and then from the pods we can access to these certificates. This is valid for the pods performing the job submission, as well as for the job manager and the task manager. The syntax at the end is the same. So from this configuration, once we have the certificate, we just have to set up the different configuration properties of Flink configuration to enable SSL in all the type of communication, we are good to go. Then the other thing that we have to take into account is the communication with the sources and sinks of data. So for our use case, we have Hadoop HDFS, Kafka, and Elasticsearch. And as we support different environments, all these services are out of our control. So the security can be set up in different ways. So we need to have a system that supports all these configurations. We're starting with Kerberos, the Kerberos configuration. So to have Kerberos running in Flink, what we need first is to be able to access the GitHub file from all the cluster components. So we proceed in a similar way as we did for the Truststore and Keystore. We are going to create a secret containing this file. Then we will expose it for all the pods so they can have access to it. And then we will add to our config map the configuration needed, the properties needed to perform the configuration of Kerberos in the pods. This is basically the Kerberos realm, the Kerberos principal, and the key distribution center address. Then what we need to do is to ensure that the pods have access to this configuration file. So by default, Kerberos is expecting to have the Kerberos configuration file in the /etc folder. But for a good practice, our pods, our containers are always running using a user that has not root access. This is this is a good practice when we run containers. So we need to make some modification when we build the image, so the user that execute the container have access to this config. So yeah, we basically what we did is that we create a template for this configuration file. We copy it during the build of the Docker image. We set the rights, the access rights to the user. And then when we execute the container using the Docker entry point, we will actually set the dynamic configuration properties to have this file with the right configuration. We do this for the Kerberos configuration file as well as for the core site XML file that is needed for the HDFS to work with Kerberos. We need to activate Kerberos authentication and specify some configuration values. And as we support different environments, what we have is that we have different flags, because we can have an environment which have Kerberos activated only for Kafka or only for HDFS or both. So we perform this configuration dynamically, and then we update as well the properties of Flink configuration to actually activate the Kerberos in the cluster. We have to have additional configuration for the Kafka consumer and producer. So when we create this, the consumer or producer, we have to specify the SaaS or Kerberos service name as well as the security protocol. So our pods that are performing the job submission, they will receive the job parameters, and from that they will add or not these properties for the configuration of Kerberos only when needed. Then we have these sources and sinks that are using SSL. To be able to communicate with them, what we need to do is to add the certificates into the Truststore of the JVM of the task manager. So as before, the first thing that we need is the actual certificates to be able to communicate with them. So we get the certificates for the different services, for Kafka, for Elasticsearch. And then we create a secret for this. We mount it in the different pods, so we have access to it. And as well here, to be able to import a certificate into the JVM Truststore, we need access rights. So again, in the Docker file, when we are building the container, we give access to this folder to the user that is executing the container. And then when we actually execute the container from the Docker entry point, we validate the flags and we perform the, we add the certificate only when we need it. We have a particular case for Elasticsearch. So we are using Elasticsearch 6. And from this version, it's only recommended to use REST actions. So the transport client is deprecated. And currently, the Elasticsearch sync for Flink 1.5 does not support the communication with Elasticsearch 6. This is only supported right now in Flink 1.6. So we create our custom Elasticsearch sync. So one person of our team was working with the community to build the pull request to include this, but this was not included in 1.5, so we are still using our custom Elasticsearch sync, but it's quite similar to the final version. So Elasticsearch is using here the REST high-level client, and it needs REST client builder to specify all the configurations that we need. For the security part, what we need to do is to create, to set the HTTP client config callback, and from that, we will specify our hostname verifier. What we are doing right now is essentially ignore this. We are saying that all host names are valid. We are relying only in the verification of the certificate chain, because as we can deploy in different namespace in different environments, where the host names can change. And the other thing that we can do here is specify the credentials to access to Elasticsearch. The username and password is if the service is configured to request a username and password. So just for information, the syntax for Flink 1.6 is very similar. We have we create a builder, and from this builder we can set the REST client factory, and from there we can specify the HTTP client config callback and do the same configuration as we did. Finally, the last thing that we have to take into account is the communication between the job manager and the persistent volume that is used for storing the checkpoint and save point data. We are currently using a persistent volume that exposes a NFS server. What we wanted to have was to have encryption in flight and at rest. This is not natively supported by our instance of NFS, so we did it in a non-conventional way. What we did was to encrypt directly the job state. So we create a custom state serializer, and from there, each time we write, we will encrypt the state, and each time we read, we will decrypt the state. With that, we have a version of encryption in flight and encryption at rest. Okay, so what next? What I talked about was the configuration of the Flink cluster, but we can enforce this security by adding security configuration for Kubernetes. So we recommend to use role-based access, as well as restrict the access to the kubectl util, so only authorized users can use this, as well as use a network policy and a pod security policy, and always have in mind that it's better to not have pods that run in with root access. And one thing that we want to explore in the next months is to use this new feature in Flink 1.5 that expose the possibility to use a single cluster, a single job cluster. So we won't have anymore job manager that is running. We will submit the job, but instead of that, we will deploy directly a single job that will contain all the information to run and only communicate with the task managers to actually execute the job. Okay, so if you have any questions.
Yes, are you deploying the individual Kubernetes pods for job manager and for task manager separately, or are you using a higher level orchestration tool to put this together, like Helm charts or something like that?
Yes, we are actually using Helm chart. We declare a Helm release. Yes, we have all the templates for the job manager, task manager, and also for the container submitting the jobs, and we deploy each time by using a Helm release. Yes.
And did you also investigate a custom Kubernetes operator for this purpose? Did you consider that?
No, we were right to use Helm, yes.
Yeah. Okay.
Mm.
Thank you.
Do you know about any possibilities to make those Flink clusters multi-tenant, so that different tenants can deploy different jobs without one isolated space in the cluster?
So to restrict the access to...
Yeah, if you would have different customers using your Kubernetes cluster and you would want to make your Flink cluster that's deployed on the Kubernetes cluster also multi-tenant so that they cannot see each other's jobs and the things they are doing. Do you know if there is something in Flink to do that?
Well, what we are using is taking advantage of Helm. From that, each time we have a different system that is deployed, we are using a different namespace. And from that, with the security policy of Kubernetes, what is deployed in one namespace cannot be accessed by other namespace. So with that, we limit the access to this cluster.
But you are not sharing. You are not sharing the same cluster for multiple tenants.
No, the idea is that each tenant will have its own cluster. Yes.
One of the last slides, you mentioned that you encrypt the state.
Yes.
How do you do that?
Well, we create a custom serializer, and in the write function before actually serializing, we are using encryption. So we specify the key and the type of encryption that we want to do. We encrypt the object, and then we write. And in the same way, when deserialize, then we first decrypt, and then we transform the job.
So that means that any writer, any developer of jobs for Flink needs to specify this as a custom serializer, right?
Yes.
Thanks.
Any more questions?
Then that's a wrap. Thank you very much, Edward.
Thank you.
Thank you. Gordon.